What I wanted to do today is to talk about the screening in R first, and then go over the questions that you might, or the issues that you might have had with assignment 3. And then basically we can extend that a little bit into the office hour. So if you have like further questions that we were not able to address, then we can just, I will just stick around and we can talk about it. All right. So, and then hopefully you all got my email, you have read my email, so I decided to change the format a little bit. So we will basically drop 1 assignment, so it will be 9 in total, to like make a little bit up for this extra time, because I thought it doesn't make sense to give you more time for this one and then you get under time pressure for the next one. So we will drop 1 assignment. And so instead of having the assignments due Monday night, I will do Tuesday night. But so that does not mean that on Monday in our lab sessions, so basically you will start asking all the questions that you have about the assignment that is due the next day. So rather, what I want you to do is the week before, so the assignment is due. Basically, I want you to be prepared to work in groups actually already on the assignments. I want to reserve some space for you to gather and to like work, basically discuss the assignment in a group that requires that all of you have worked on it individually already. And then if you have like additional questions, I'm happy to talk about them in the subsequent office hour. And then so basically the following Monday, so the Monday before, so the assignment is due, that's just some so it's like some real emergency, you detected some like last minute problem or whatever. So then so that is basically an extra safety net, but it's not meant to be the main day for working on the assignment. All right, so I hope that'll help a little bit. And so yeah, and then please use the so also use the discussion forum, right? So that will be helpful as well. Then it also gives like an idea what others are struggling with, and so that helps to structure the lab sessions a little bit. All right. So before we're going to talk about the current assignment, as I said, I wanted to show you a little bit so how we do data screening in R, and we'll also recap a little bit on what we talked about in our last R lab. So basically, it's always like a little repetition, right, of the things that we have done before, and also sometimes I show you like a few new things, so the majority of data screening, though, we will do when we talk about the individual statistical methods. So for example, when we talk about multiple regression and how to do it in R, so we will talk in very much detail about how we do the data screening, how we check the assumptions, right? So that is part of the whole thing. And so I think it would also be a little bit more meaningful, so you have a better understanding of the statistical method itself. So many things also in the and checking the assumptions are based on concepts of regression, etc. So I think it will be helpful if you have the theoretical background to understand better what's going on and what the purpose of all of that is. All right, so we are working with an HTML file again today. It's a screening file. So that is already on Blackboard. So let me share my screen actually. I will just share my entire screen. That's always easier. And let me pull up the file. Can you see it? Can you all see screening? Okay, super. All right. So then hopefully you've all installed the packages so that we're going to need today, so that we don't have issues with the installation. And so then you can all load the packages that we are going to use. And I always expect that the packages we have used in previous sessions, that you still have them installed on your machine, so that you don't have to reinstall them, right? So that make sure if you update R or something happens to your machine, that you always basically reinstall the packages that we had before. Okay. So, and the first thing is that we're reading in, or we're importing our data set, right? So our screen text file. And so you can do that using the read.delim command or function in from R. And then you just put in here, so that is my path, obviously. So here you have to, if you have it in your workspace, then you can just put type in the file name. If you have it in a different directory, you have to put in the entire path. And so then there's a file name. So keep in mind, right? So the direction of the slashes depends on whether you're working with a Windows machine or with a Mac. And so we want the headers, right? And so you can give it whatever name you want to. I call it screen data frame, screen.df, but you can give it the name of your liking. Just have to change it then throughout the tutorial. Okay, so please let me know. I just want to wait for you to basically. I just want to make sure you all have it in your workspace and you have the variable. So please just let me know. Oops. Yeah, if you could just indicate in the chat that if you're done.
I'm sorry, is this posted on Blackboard? Because I'm trying to type it and then I thought about this is similar to like last lab and I could just copy and paste like last time. Is it posted on Blackboard?
Yeah.
Or
yeah.
Okay, let me just go back. I'm sorry.
It's on Blackboard. So it's the screening. It's called screening.html.
Okay. Dr. Quick question. Library pass decks, what is that under? Because I've downloaded Mice, HMISC, Final Fit, and Psych, but
that is just it's not mandatory.
Yeah, because it gets error, that's why.
So I just want to show you an alternative that I prefer for descriptive statistics. So you don't have to. I mean, if you want to use that, you have to basically do the install packages first. So you have to type in install packages as tags, and then you can load it.
Okay.
So, but that is just an alternative I wanted to show you. So it's basically just.
All right.
I just needed.
But everything above DigiPlot2 is good. Okay.
I need it for within this script here to show it to you, but it's not essential.
Okay. it gave me an error. So we renamed read the line whatever to the path name, our path name, right?
Or you can just put
Okay.
it in your, you can just put it in some folder and make that folder your workspace. Then you just have to put in the screen dot text or whatever you called it. So
Yeah.
yeah, for all of you who are having like horrible issues with the path name, so you can just throw it in some folder of your liking, and then you can see mine, right?
For me, it works to
Move that a
just
little bit.
use an import option that's under the File tab in Windows.
Sorry, I didn't get that.
Oh, sorry. So what I did was I used the import option that's under the File tab, but I'm using Windows, so I don't know if that's the same for Macs.
Okay, so you can also go to Viewer, right? Sorry, to Files, and then under More, you basically you just navigate to the wherever you have the right. So even if you have it in Downloads, right? So you navigate to the folder that that has the file, the text file in it, and you say set as working directory, and then you can simply replace. So you basically can drop this entire part here and just have to type in screen.txt or whatever the name of your file is. So, and then it should be able to read that file. Yeah, and then let me know in the chat whether you're, otherwise you'll be sitting here another 30 minutes. Okay, super. All right, another lesson for me. Next time, also make sure to give you instructions to basically load the file so that you can save some time in the lab. Yeah, sorry about that. It's often so.
I'm sorry.
The little things that are taking more time than I anticipate.
Matt, you said to import the data file because I tried doing it a different way and copying and pasting the file path, and it keeps giving me an error. So import it from where?
Yeah, so on Windows,
yeah.
No, because I have a PC, so that's why I'm trying to like figure it out.
Yeah, so under Files, File, there should be an option for Import Dataset, and then you could just get the file from there.
Oh, okay, I see. No, that's not what I meant. I meant the second part. You could still do that, import data set, and do that into the second part, where it says screen.df, read the lim, and then do that. That's what you're saying?
Oh yeah, that's basically the same thing. It writes the code out automatically.
Okay, all right, thank you. And then you copy it from the text. Gotcha. I'm sorry.
Oh yeah, but then I think you'd have to make the Tibble part by yourself though.
Yeah.
Dr. Unger, I was wondering, what does header equals true mean?
This just means that the variable names are read in as the basically the column names in R.
Thank you.
It might be the default. I'm not actually 100% sure. It's probably the default. I just like to add it. Alrighty. So are you still working? I'm working on it, or are you all set? Okay. So it should be relatively foolproof as long as you have the text as I just showed you, right? As long as you have okay, I see it. All right, super. So you can also, instead of like using the import function, you can simply put it in any folder. So wherever your screen.txt is sitting, and you set using the, right? So the R function here using files, you just navigate to the folder where where the file is. And then you set that as working directory. Yeah? So you set as working directory, and then you have to just put in the name. Oops, sorry. So and then you just have to put in screen.txt and right, quotes, and it has to read it then. So then you cannot even have issues with the direction of the slashes or whatever perks the. All right, Kimberly, are you just let me know. We're still working on trying to basically so to get the screen.df data frame in their workspace. You're all set. You're all done. You have to tell me, otherwise I will sit here in silence for the next half hour.
Yeah, no, it's still giving me a freaking error. That's why I'm like,
what is happening?
I go to files, I see the screening date, the data file. I'm right clicking, it's not happening. I'm trying to see on the way you did it on a viewer. I can't seem to copy it from there, and it keeps giving me an error. So I'm like, okay, what else should I do?
Yeah, so you go to the folder. You have to select the folder that has your directory, right? So let's assume here it is. So for me, under teaching, right? So then I have
no, I saved it under documents, and then when I see on the files on the folder, like on files on the console on the side, it's already there. Like I see it, it's there. It's screening.dat.
In the environment, or where do you see it?
In the in R.
Is it?
Yes.
Look at my screen.
Yeah, like
it's just the environment.
No, below where it says files.
It's under files.
So I already have.
It's not R.
It's under files. It's
on
already
your computer, right? It is on your computer. And what you have to do is you have to find the folder, right? So let's assume it's for me it's in the IBM folder, right? So I would click on it. So that's all not a good So here in my lit folder, right? So here, ignore the other files. It would be, then I say, okay, perfect. So so that is my working directory, yeah? And then say set as working directory. Click, and see that in R is, oh, sorry. So that is basically, it's not doing the, see, I never use that. Actually have to go one down. So then I have to go
There we go.
in my lit folder, and I say it's in here, and I say again, I never use this option. So then I say, look, set as working directory. See, now it's basically setting it to this folder where you basically can't even navigate to a screen file, right? So when you see it in your little window, then you click set working directory. So then this is what R is doing here. And then you can use this code. You just remove everything here. You remove that.
And then remove that.
The first, right? So this first part, everything, you just keep, everything that I highlighted, you move. You just keep screen.txt quotes, and then it must work. So otherwise, that would be very surprising.
So delete this part. Gotcha. Got it.
Okay, super. So great. Let me just close the chat so I can see something here. All right. So, okay. So after we have our screen DF, right? So in our workspace and our environment as a data frame, but we want to make it a tibble, right? So and then just a reminder, we can do that using the tibble function, right? So tibble, then we're giving our data frame as argument, converting it to a tibble, and then we just want to get rid of the first column, right? So that you see just subject number, so some sub-no or so sub-no. Right, and that, so just a reminder, it was called a pipe, right? What is a pipe operator doing? So it's taking what's on the left side, which in this case is just our tibble here, or data frame, and it's giving that as the first argument to the function that's on the right, which in this case is a select function. So we tell select, so from our tibble screen.df, remove the first column, and so the function knows it's removed because we have the minus in front of the one. Yeah? So we could also spell out the name of the column if we wanted to do that. And then in the next line, it is just basically so to the first way to look at the data. So you see that so the names of the right. So we do no longer have the first variable. So the variable names, the column names are these here. Yeah, we'll talk about that in a second. And then you can also take a look at the first few values for these variables using the glimpse function. And so you can see it's 465 rows. So yeah, quite a big data set. So it's 465 cases. We have 7 columns. And so that is all integer, right? So we have all integer in these columns. And then so they have a little bit cryptic names. It took me a while to decipher. So the first one is actually visits to health professionals. Then the second one is attitude toward medication. So the add drug. Then add house is attitude towards housework. So then we have income, employment status, marital status, and race. Which race is a little weird. It has just 2 values, but I mean that is just a data set for like practicing, right? It's not necessarily meaningful. All right. So and that is always a good thing, right? So if you just especially for big data files, if you just look at the first, you could also use a header comment or whatever, right? So to just take a look what you have in there and whether it's meaningful, just to double check that you don't have like all zeros or all NAs, or right. So that's a basic import worked as it was supposed to work. You can of course also always look, so use a view argument, and then you can look at the data file in R directly as a view function, sorry. Okay, so let's first take a look at missing values. All right, so when we are checking our data file. And so we can do several things. It's always a good idea to look at the descriptive statistics, also to check whether the data is plausible, right? And I mean, what I haven't included here, right? We were talking about that last week, is that you always check subsets of your data, whether they make sense, right? So for certain cases, or for a subset of your cases, that you really check each individual value for each variable, whether it corresponds to either what your questionnaire data was, or what your experimental software exported, right? So to make sure that it's really, that there's not like sometimes there might be things like the rows are like just one down, or something is got mixed up, right, in the whole process. Okay. So, and we are, so in order to look at some basic descriptive statistics for all our variables, we're using the describe function that comes from the Psych package. And here, that is something that I mentioned quite a while ago, you might not remember it. So there are actually a lot of functions so that have the same name in R. So you have functions that come from different packages. And so, for example, there's several describe functions. So one is in the Psych package, but another one is, for example, in the HMISC package that we have loaded as well. And so if you don't tell R otherwise, so it will always use the function of the package that you loaded last. So the library that you loaded last. So in this case, we loaded probably the HMISC last. And that means it would use the describe function from HMISC. We don't want that. If you want to force R to use a function from a certain package, you have to do it like that. So you have to write the package name first, then the two colon operators, and then the function name as usual. Right? So that way R knows what function to use. So, and as you can see here, so the first column just gives you the index for the variables, so the first, second, seventh, etc., etc. So the variable name, and then you have the number of cases, right? So here in each variable, you can already tell that. So we have here one missing value for at house, or attitude toward housework. Yeah, I don't even remember. And then income has quite a few missing values. So then you have the mean, right, for each variable. You have the standard deviation. You have the median, so then you have the trimmed mean, so that's always, so the default, you can also set that, right? So if you look up the, so the help menu for describe, so you can change the, so the cutoffs for the trimmed mean, so that basically just, I think the default is 0.1, so it cuts off the lowest and the highest 0.1% of your data. So basically the lower and the upper tail of your distribution, right, and calculates the mean without these extreme values in the distribution. So the MAD, that is the, as I have described it here, also below, that is it's a more robust statistic that is more resilient to outliers than the standard deviation. So it's basically, it's called the median absolute deviation. So which can be useful. So a few outliers are relevant for this measure. So it's basically not as influenced by rare values that are completely off range. Right, then you have the minimums, the maximums, the range. So small, largest minus smallest. You have the skewness, the kurtosis, and the standard error. Right, so for the actually, I'm not 100% sure. I almost assume it must be the standard error for the mean, but I'm not using the describe of the Psych package that often, to be honest. But it must be the standard error of the mean. Just a little bit, I would basically put it here probably. I'm not sure why it's the last one here. Anyway, so okay, all right, and so that gives us a lot of information that all looks relatively reasonable. So we can see here already the time DRS, so time spent at doctors. I don't know what this variable name is supposed to code. So it has a relatively large value for skew. So for skewness, so it has a positive skew, right? So remember, so the normal distribution has 0 value, right? So for both, for kurtosis, which should be called excess actually here. So for both skewness and kurtosis, so you can see that, so this is already a variable that is most likely not normally distributed. So here we have relatively strong deviations of a race. So you can more or less ignore that because race is this binary variable, right? So we have several others, but it's most important for those that are continuous. Okay. So, okay. So, right, I also mentioned that here in the text, right? So if you want to check whether they're outliers and whether they contribute to skew of the data. So you can also compare the trimmed mean with the actual mean, and if there is a significant, so a large deviation, so that is also an indication, right? So that you have a lot of outliers, and you can see that this is the case very much for the first variable, right? So maybe you have a huge difference between the trimmed mean and the mean. Okay. So right, I mentioned that already. So, and this is just for illustration purposes, right? If you would have just called describe screen df, so we would have gotten a completely different output. So, right, so it's also organized in a different way. So it is a descriptive statistics as well, but it is a descriptive statistic function from the so the HMISC package, and it organizes the output in a completely different way, right? So it also doesn't give you the information for kurtosis and skewness. Instead, it gives you the percentiles here, right? So it gives you the 5th, the 10th, the 25th, the 50th, the 75th, the 90th, and 95th percentile for each variable. So then it gives you the lowest and the highest scores. So it can be useful, right? Just slightly different. Okay. So, and I mentioned that I think last week, unfortunately, I told you the wrong package, right function, wrong package. So you can, and that is my preferred function actually. So you can also use the stat.desc function from the PASTEX package. So which has a lot of useful information. So if you give that function, so basically you have to specify whether you want the basic descriptive statistics or like a more comprehensive version of. So basically it gives you more descriptive statistics, but then you have to set the basic argument here to false. And so the norm argument here asks you whether you also want statistics for normal that are relevant for normal distribution, and you have to set that to true. So these are both in the, if the default is basic true and normal false, right? And in R, I did that several times already. Instead of really writing out false and true, you can also just type F and T. Okay. So, and as you can see, right, so it gives you median, means, a standard error for the mean, as a confidence, a 95% confidence interval for the mean. You can change that in the arguments here as well, which you can choose any confidence interval. So it gives you standard as a variance, a standard deviation, so, and the skewness. So these are, it's actually nice, it's convenient. So these are two standard errors for the skewness. So if that value is larger than 1, probably it's also an indication that so the variable is not normally distributed. And so it also gives you the result of the test for normal distribution. So here's the Shapiro-Wilk test that is implemented in this function, and with a corresponding, so this is just a test statistic W, and this is the corresponding p-value. And you can see so that the p-value here is smaller than 0.001 for all variables. So, and that illustrates a problem that I mentioned last week in class, that for large enough samples, so the normality assumption, or that's almost violated, even though the deviations are completely irrelevant. So even it's like really just a minor deviation from normality, so the test will be significant. Of course, as you know, right, with increasing sample size, you have much higher power. So even minor deviations will be will come out as significant, right? So, and that's why it's for data sets of that size actually not that meaningful to look at the, it's a statistical test. It's better to plot the data and to see whether they are normally distributed or not. Right, and if you, I hope you, in case you're not familiar with this notation, so the E minus 30 here, that is basically just a power function. So it always means to the base 10, right? So this is in English, what is this? Is 10 to power of 30? So what is the right way of saying it? I keep forgetting. It's actually one of the few things that's easier in German than in English. So is it?
The negative 30.
Okay, all right. So, and that basically means that you have to move the decimal point 30 places to the left, right? So, and that means that it's basically 0. So it's a super small number. That is not surprising because we already saw, right, that for time DRS, so the skewness and the kurtosis were far from being normal. So that is not super surprising. But even here, right, it's all, these are all really small numbers. So they're all almost 0. As I said, for the binary variables, for the categorical dichotomous variables, it doesn't make sense. But so yeah, so for samples of that size, a statistical test for normality is not that informative. Okay, so all right, but we know, so basically moving on from the descriptive statistics, so we wanted to identify actually missing data. And a function that is very useful in detecting patterns of missingness, which we have learned right last week, are very important. So whether they're missing completely at random or missing at random or not missing at random. So you can use like really nice functions that are implemented in R, like the one here that is called missing plot. And so you see the row number on the x-axis here, right? So these are your observations, your cases. In this case, this is just participants, but it depends on your data, right? So what you're recording. And then you have all variables on the y-axis, right? So all our 7 variables here on the y-axis. And then you have lines for each case of so where you have a missing data point. And so we see that we have quite a few for income, and so but only 1 for so attitude toward housework. So here, because it's just a few data sets, so few data points that are actually missing. So there's not really a pattern to detect. But if we had like a bigger data file, we will see that later when we're actually working with more realistic data sets and doing more meaningful analysis. So we will see how so the missingness pattern can be detected with this plot. So that is mostly to introduce the methods to you and the general layout, how it looks like, right? So we don't want to overwhelm you with too much interpretation right now. Basically, I want to show you the options and that you have seen it and know the code, and then later we will talk about so the interpretation and the meaning. And so here, basically, it just confirms that we have missing values only on 2 variables, and so they're most likely unrelated because so there is not much missing, right, in most of the cases. All right. So and we also know that if we have fewer than, so it's just a rule of thumb, right? So if we have fewer than 5% missing values, then we might get away with just excluding them. So especially if they're completely missing at random. If we have more than 5%, so then we definitely have to look whether what's a missingness mechanism is, right? So to determine what the best way is to deal with those missing data. And so, right, so otherwise we can, as I said, so we can just delete them. And here, so this is basically just the command to do that. So that this apply function is a very useful one, so that you will use a lot when you start actually working with R and doing all your analysis. It's basically when you can use that to iterate over your data frame, right, over different rows or columns, and apply a certain function repeatedly, right? So on subsets of your data, so either on all rows or on all columns. So that's very useful, right? So that, but don't sweat it right now. So it's just to introduce the general idea to you. So what we can see here is, so that is just the percentages of missing data. So which is 0, 0, 0 for most of the variables, and we see so for attitudes towards housework, it is a very small number because only one value was missing, but then for income it's over 5%. Right, so slightly over 5%. So that means probably makes sense to look a little bit more closely into that. There's another actually really useful function inside the mice package. The mice package is a package that does the multiple imputation that we also talked about last week, right, as a standard for like imputing missing values. So if you choose a method for your data set and you have more than 5% data missing, and especially if there's reason to believe that they're not missing completely at random, if they're not MCAR, then you will most likely use multiple imputation, right? Because it's superior to all other methods. So the mice package is doing that. So it has this functionality implemented, and also has this really nice function md.pattern that also allows you to, it's similar to that, just slightly different representation. It basically allows you to graphically represent the missing data pattern. And so, and here in our table, we see that so that we have 438 cases that contain absolutely no missing values, right? So that's the first row here. Then we have 26 that have missing data on the income variable only. And then we have one case that has missing data on the attitude towards house work. All right. And so we have also talked, so last week we have talked about so how we can run a statistical test to determine whether so the data are missing completely at random or only missing at random. And so, and I told you that there's actually a test has been developed by Little, so that is implemented in R, and where we can test basically whether the missingness in one variable depends on other variables in our data set. So for example, we have a lot of missing values here in income, right? So we can test, does it depend on time DRS? Does it depend on ad drug? So can these variables predict whether, this, right? So whether we have a missing data point in on income. So unfortunately, the package that used to contain this overall omnibus test, where you basically test for all variables simultaneously, is no longer maintained. So they are developing a new package that that has a function implemented, but it's currently only in the developer's version. So it will come soon, but right now it's simply not available in R. So we have to do it individually for each variable, right? So which is not a big deal. So you basically you can use the nice, so also, right, so there is a package that's called gGALI. I never know how to pronounce them, but it's this gGALI package. And so it has two functions that are really useful. One is the missing pairs function. So we will talk about another function later. Hallo Aden. Na, mein Schätzelein. Hast du das draußen gefunden oder ist das dreckig? Okay. Marvin muss jetzt unterrichten. Okay, so basically what I'm doing here, so I'm using the missing compare function later on. Wait a second. So maybe the text here doesn't seem to correspond to what I'm doing. anyway, I thought I'm using both and one just later. Okay, so but it doesn't matter. So what we first have to do is we have to define what our explanatory variables. So the explanatory variables in this case means that so those are the variables in our data set that we have observed and that are the predictors. So, and what we want to predict is a missingness, right? So missingness on income. So we're simply just defining so what variables here are used for our prediction, and so what is a variable that is for which we want to predict the missingness. And then so we're using actually sorry, the missing compare function. So and just give it as the arguments, of course, the screen df, so our data set, and then our list of so the dependent variables, which is in this case only one, right? It could also be several, and the list of so the explanatory variables, and so that is just to make it look nicer, right? It's just to give you the table here, so you can ignore that. So it would work as well without so this last row here. So it just makes it a little bit nicer, the output test. And so, and then the nice thing about missing compare is that automatically, depending on the values in your variables, it will automatically select the right test statistic. So either a t-test or a chi-square test, right? So if you have dichotomous variables, binary variables with only two values, it will choose a chi-square test. If you have right, so like a numeric variable with more values, then R will interpret that as a continuous variable and then do a t-test. Okay, so what we're seeing right here, so it's always the mean, right, for so cases that have no missing data and that have missing data on income, right? So it compares for all these variables, for all these predictors, whether the mean of basically the mean for cases that have not reported their income is significantly different than the mean of those cases, those participants who have reported their income. Right? And if that would be significantly different, that would indicate that time DRS is a predictor, so that basically it predicts a missingness of income. So which would indicate that we have data that is not completely missing at random. So in here we can see so that none of these p-values here is significant. So and so that means we can go ahead with our assumption that the data is missing. So MCARs are missing completely at random. But so keep in mind, we keep that assumption. We cannot be 100% sure, right? So we just we maintain it for now. So we have no clear evidence that so tells us that's not true, right? So at least, so it doesn't seem to be the case here. So, but it's still possible that, so there's some other variable that we actually have not measured that predicts the missingness, right? So, but just in our data set, it doesn't seem like it depends on the other variables. Alrighty. Okay, so here we also get this warning. I have included that on purpose. So it says a chi-squared approximation may be incorrect. And the reason for that is that for race, we have a basically we have very few values in one of our 4 cells, right? In our 2x2 table. So if you look at that, so basically if you look at the breakdown, so for how many cases we basically have in each of the combinations between race and missingness, then you see that I think there's only 3 or 4 values in one combination, and that's just not enough to basically we have too little data for the chi-squared approximation to be correct, right? So that's why you get this warning. So you don't have, remember, right? So we were talking about that as well. So we simply don't have enough data in at least one of the cells. And so we probably have to run an exact test or do something different, but so this might be misleading, right? So this test statistic. All right. Actually, I was lying to you. It's not doing a t-test. It's doing a Kruskal-Wallis test. So it's doing the non-parametric equivalent for a t-test, actually non-parametric equivalent to a one-way ANOVA. So because you can have more than 2 groups that you're comparing. So it's actually quite smart. So it does not, because a t-test assumes, right, that you have normality. And so that doesn't need to be the case here. So that's a good thing, right? So it's automatically running a non-parametric, more general version. Okay. So, but you can, if you want to, for U data, you can also use a t-test, right? If you do it, if you have your own implementation or do it by hand. Okay, so, all right. So what are we doing with our missing values, right? So we have talked about how one option is to simply delete cases or variables. So in this case, so we could just drop any cases that contain missing data. And we can do that using the function na.omit, right? So if you give that the data frame as a variable, as an argument, so it'll just remove all cases that have missing values. And so in our case, right, so we would get an object that is only 438 rows. So it would just remove all the cases that have any missing values on any variable, right? So in this case, it's only 2, but depends on the data set. Okay, so right, if you do that here, so we are again, right, so we use the pipe operator. So we're giving na.omit our data frame as an argument. And then, so as a result, we are asking what is the dimensionality of this data frame, was this tibble, right? So it's the one that has where all the missing data and missing cases, as the cases with missing data are deleted. And you see we have 438 rows and 7 columns. And of course, we did not delete any variables, but we deleted all cases that have missing values, missing data. Okay. Or if you wanted to delete the variable, if we say, okay, income is irrelevant for our analysis, so we can just get rid of that. So rather than sacrificing our data on the other variables, for those cases who don't have any data there, we could simply just get rid of income, right? And then we have a larger data frame, right? So because so we preserve these over 30 cases that have no income data reported. Okay, so and this is just, so this imputing here, I included that for demonstration purposes only, right? So how to do it in general, it is in this case not particularly meaningful, but just to go over the steps how to do the multiple imputation. But actually, before we are talking about multiple imputation, I wanted to show you something that's easier. So the mean substitution. So remember, so one way, one super easy way of just replacing missing values is to substitute. So basically, to substitute the NAs with the mean of the variable that is affected, and so. Right, and in this case, what we are doing here is first simply create a new variable. So because I don't want to change this data frame here, so I create a new variable and assign it. So the tibble here is basically just a copy, right, of our tibble. And then I'm creating a vector that is called the na.idx. So these are the indices. So this vector will contain the indices of all cases that have missing data. And so basically, how do I construct this vector here? So again, I give it our data frame. I say select income from the data frame. Okay, that's my dear.
What is that?
I don't know. Okay, du musst mal wieder rausgehen, mein Schatzelein. So I give it the the screen as it, so our tibble as an input argument. I select the income variable from our tibble, and then so I'm basically using that as argument to the function is.na, and that is basically just so it checks for each element whether it is an AA, whether it's a missing value or not. So it's basically just a vector of trues and false, right? So it says true, 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 false, 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 depending on whether certain case has an A or not. So this is this vector here, right? So that we are creating. And so then I'm using this vector later on to define where we actually want to replace values, right? So, okay. I'll do that step by step. So what I'm doing here is to first to calculate the so the averages, right? So so I call that yeah, my variable names are also not always very so, but it's called means. It's supposed to say means by employment status, right? So I basically want to make it a little bit more difficult, and I say, okay, so what I want to impute here is not only the mean of income, but I want to impute the mean for each employment group, right? So yeah, Matthew, go ahead.
I was curious about something. So renaming screen.df to screen.imp, does that change the file type, or is that merely just to differentiate the two?
It's like a copy.
Okay, so it's just merely a matter of differentiation. It doesn't change like the data frame into a different type of file, right? Oh,
No, just
thank you.
really just a copy. So, okay, all right. So I'll make it a little bit more difficult. So I'm trying to explain so what I'm doing here. So rather than just substituting with the overall mean of income, I want to substitute it with the mean for each subgroup based on their employment status, right? So depending whether the participant that has a missing value on income is employed or unemployed, I want to replace their missing income with, so if the participant is unemployed, I want to replace their missing value with the mean income for the other unemployed participants that have income data. And if they're employed, then I want to replace their missing income with the mean income of employed participants that have answered that question. Yeah. So, okay. And basically, that's what I'm doing here with the AVE function. So, which takes as input the so the variable that you actually want to, right? So that you use for your calculations and later also for the imputation. So then you use, so basically the second variable here is the one that you use as a grouping variable, so which in our case is employment. Here you define the function, which is in our case a mean, right? So so this is basically all one argument here, right? So where you define the function, and so that is the mean. So you basically, right? So it's mean x. So you say it's function of x, right? And you say mean x, and so remove missing values is true. Right? That's also very important because otherwise you cannot. So you would get an error message here because I would say I cannot calculate the mean. All right. So and then I will basically just put that into, so this, what I have calculated here, right? So for all data, for all our cases here, for the entire, for all, right? So it's all rows in our data frame. So I want to put that in, and those rows that have actually missing income data only. Yeah, so that's why I'm selecting only the subset of rows where, right, that have a true in this vector. So basically that's a vector that has a true for whatever row has a missing value, right? And so, and these are the ones that we want to replace, right? And that's why we have that on the left hand side here of the assignment operator. And so what are we putting in here? So we're selecting the income variable, right, from our screening data frame. And then we are using this, so the function that we have defined above here. And so we're basically subsetting our our rows that have where the data is missing, right? So that means we are pulling from this vector here that is created by this function, right? So we are pulling only those values that correspond to the row numbers that have no income data, right? And those we apply to our original data frame. So sorry, that is basically meaningless here. That is just to pull out. So I did not use that. I probably wanted to write it in a different way. So it might be a little bit confusing. So this is just the function that calculates the mean income per employment group, right, for all cases. And you're calling this function again. So what you're getting is a vector, right? It's a vector that has for each case in the data set so that basically calculates the mean income by employment group. And then you're taking from this vector here that is calculated by this function, you're taking only the rows that have missing values, and then you put it in your original data frame. So it's a bit hard to explain, but it's actually not difficult to do. And so if we basically look at income after this step of the mean imputation, we see that we now have no missing data anymore. So, and we have 465 cases, right? And so basically we got rid of our missing values. Okay. All right. So after we demonstrated that for the mean substitution, so I wanted to talk a little bit about some multiple imputation. So and for multiple imputation, we are using the MICE package, and the MICE package is actually very, very well documented. So you have a lot of like extra tutorials on it, and with a lot of advice. So, and it's really important to study it very carefully before you do it on your own. So, and it's a heart of the MICE package is a function MICE that basically it calculates your imputations. And so this MICE function takes a number of different arguments, but so what we're specifying here is a little bit limited. So basically, so what we're working with is so the argument m, and that is the number of imputations. So here, because we are missing relatively few data, so 10 iterations should be sufficient. So normally, so we want we want a little bit, it's not iterations, so 10 imputations should be enough. So then we have the second parameter, that is the maximum number of iterations. So that is per imputation, right? So per full set of estimated missing values. And so you may remember so that the multiple imputation uses an iterative, so an approximative algorithm, so it has to converge at some point, right? So it runs through multiple iterations to get closer and closer to the estimated values. And so you usually want to limit the number of iterations because it takes longer, right? So the more you have, but it's also important not to set it too low, because then so you might just arrive at some local minimum or maximum, but there actually it might not be the ideal estimate for your parameter. So that's why you always want to make sure so that you basically that your estimates properly converge, right? So that they, I will show you in a second what that means. So the seed argument is just a random seed parameter. So that is useful when you want to reproduce your results, if you want to get the same imputation. So imputations, every time you run the function or the call, you can just assign it whatever number you want to. Right, so that's completely arbitrary. So I chose 1, 2, 3 here, but you can give it like 500, 5, whatever you wanna do. Okay, so if you don't define the seed, so then with each function called, you will get slightly different results, right? So they will always vary. Okay, and so what? Okay, so I'm just looking for my something is missing here. So I wanted to actually put this function here on top. That's a little bit annoying, but anyway. So if you, maybe we can do that first here. So when you call mice with the following parameters here, right? So with our data frame, that's our data, then the number of imputations is 10. And we have 20 as a maximum number of iterations. And then we did not specify so the predictor matrix argument here. So basically we just wanted to set the seed, and so this you can ignore as well. So if you run that, basically this line, but without the predictor matrix and without the printf, so then you will get some result, but so this result will automatically include all variables in your data set as predictors. So, and it will also try to do imputations for all variables on your data set, which is not meaningful, right? Because we are not, because all variables except for income and attitude towards housework don't have any missing data. So, and that's why, so the mice function gives you the option to define your own predictor matrix. So with the predictor matrix, you can control what variables you're using as predictors and what variables you're using as outcome variables. So for which variables you basically want to predict, or estimate the missing values, and what variables you're using as basically as your input to predict these values, right, as your predictors. And so if you have run hopefully this this function here below, but just as I said, so excludes the predictor matrix element and the print. I mean, print it doesn't really matter. So if you then call the, or pull out the so your predictor matrix here by using this command here, right? So you just have to pull out pred. Then you'll see that your matrix looks like that. So it has ones in each position except for the diagonal here. So, and each variable in this predictor matrix has a row and a column. Yeah, so, and if you have a value of 1 in your predictor matrix, so that means that the column variable was used to impute the row variable, right? So if you have here, so if you have add drug 1, so that means that so the what is it again? Attitude to what's medication? So add drug, so the variable add drug was used to predict time spent at doctor's offices, right? And so on. So basically these here, the rows are always, so this represents the the variables that are being predicted, right? So that we're trying to impute missing values, and these here are your predictors. So these represent the predictors that you're using in your model. So that means if we don't want, right, we only had missing values in time DRS and add drug, right? So if we don't, sorry, we only had missing values in income and at house. So if you don't want so these other values, these other data if you don't want the model to estimate basically the missing data for these variables, we have to set all the weights here, all the predictors to 0, right, for a given variable. So here time DRS, attitude toward drugs, so employment, marital status, race, so they all did not have missing values, right? That's, we are setting the weights here all to 0. And just for at house and for income, we are setting the weights to 1, and we are basically, I mean, despite the fact that the probably it doesn't make that much sense for this example. So here we're including all variables as predictors, of course, except for the variable. I mean, the variable cannot predict itself, right? So that's why income here has a 0. But here we see that, right? So that the 1 represents it. So time DRS, at drug, at house, employment status, marital status, race. So they're all used to predict the missing values, and at house and the same for income. So that is how you manipulate your predictor matrix. And you can do that here in this case very simply, right? By first selecting the rows, right? So you can just give it this this vector here that simply has the names of the rows, and then so you use this notation here to make sure that it's that refers to all columns, right? So and you set them to 0. Yeah, so that's what we did here. We basically just set this row to 0. We set this row to 0. We set this row to 0. If you want to do it the other way around, if you want to exclude predictors, then you have to specify here behind the comma. Then you have to specify the variables that you would want to exclude from the prediction model. Yeah, so that you don't want to use to predict the missing values. Okay. So, and now we can run our model again, right? So, and now we are specifying an additional argument, so the predictor matrix. We're setting that to the matrix that we specified here. And so this printf is just so that it doesn't print out all the iterations, so to save us a little bit of time. And then you can ask R for a summary, and then it will give you some information. So you will see that the class of the object is, the number of imputations, we set it to 10, so not very surprising. It also tells you what method it used. So that is the PMM method, that is the default so basically if you, for the mice function, if you don't specify it otherwise, right, but there are like many other options that you can use. And and then it also prints again for you as a confirmation that it was all correct, the predictor matrix that it used. Okay, so now we are coming back to the proper number of iterations, right? And whether, because it's an iterative mechanism, an iterative algorithm, so there's a chance that things might go wrong. So and so what you want to do is, so you want the estimates for all variables to converge, so that they basically getting closer to the same, or that they, right, so that they basically, that the estimates get more similar, or not, that at least that they don't diverge across the different iterations. And so therefore it's always good to check what's called the trace plots for a few more iterations to make sure that you don't have any divergence, right? So that you don't have any trends where so for like later iterations, so the number actually go for the estimated values go in different directions. So what you can do to check your, so basically the convergence of your estimates is also a nice function. So it's called plot. So you just call the plot function. So within mice, right? It's not ours base package plot function, it's plot function as in mice. You give it the, so your MITS model, or your estimated model as argument. And that will print for all the variables that were imputed so the mean and the standard deviation of your estimated values across all iterations. So so each data point here is one iteration. So we had 20 in our case, and here you have the values, right? So for at house, that varies between 10 and so this is 34, and for income between 3 and 5.5. And what you normally want to see is that so we would like to see the different streams here intermingle, right? And so we want them to be free of any trends for later iterations. And that looks okay here in general, right? So what we don't want to see is that basically one, so that one stream here goes in a completely different direction or so, later. So we want to make sure that they're all like just randomly fluctuating, and that basically not one goes like off here or here, wherever, right? So that they basically just randomly fluctuating around some value, right? So and that is important to check. So these look okay. I hope we will have a data set later where they don't look so great. So the reason that we have no standard deviation here is because we have only one missing value. That's why I couldn't estimate the standard deviation, right? So that's why this is empty here. So we have only one value to be, so that cannot have a standard deviation. Well, that's the reason, right? So at house had only one missing value. All right. Okay. So if you actually want to check what are these, so what for each imputation, so what are the values that so mice package came, or this algorithm came up with, then we have to go inside our the MIPS object. So and we basically use our dollar operator again, right? So we're first accessing the imp field within so our MIPS object, and then we are accessing the income field. So within imp, so it stands for imputation. And then we see here, right? So these are just our cases with missing values, and these are our 10 imputations. Sorry, not iterations, imputations. And then you can see, right, that so these are the the estimated values for income. So here, so in the first iteration for case 5, it estimates 4, 4, 4. That's quite deviant, right? So here it estimates 8, 4, 4, 7, 4, 2, 1. Okay, so then for the next one, it estimates like 6, 5, 3, 4, 9, 3, 1, 2, 3, 5, 1. So I'm not sure what's the income, how it is measured. It's a little bit odd. So these, I think it's numbers from 1 to 10. Not 100% sure what it means, whether it's like from, I don't know what's the data, how the data is generated. So, but you can see there's quite a lot of variation, right, from imputation to imputation, right? So and yeah, so and what so what we also want to make sure is that so our imputed data, of course, are plausible. Yeah. So and another check that you can make to see whether they are plausible is just to look at the distribution of your estimate, so of your imputed, so the estimated values, and see whether they are significantly, right? Whether we see some pattern. So that the distribution is different from the observed values, right? For the same variables, and that can be done by the function strip plot. It's also very helpful here. So again, so the arguments are our MIPS object, so the estimated basically the object that has all the imputed values. And then, so here we are just specifying that we want that for the variable income. And so that is basically estimated from the imp. So that is some basically inherent argument, so that the strip plot function can understand. So it's basically referring to this field here of the object. And so this is just defining how large the dots are. And you can see here, right? So for each imputation, so the first one is basically no imputation. That is just the original data, right? And then so here you see that goes until 11. So here you see our 10 solutions. So the 10 different imputation models. So then again, just a reminder, right? So each imputation is basically a data set that has where we have estimated the missing values, but they are different each time, right? So each individual data set is an estimation, and they are all different. So they're different possible scenarios. What could be possible, right? So what could be plausible values for these missing income data? And here in red, So you see these are the imputed values, right? So the red ones are the imputed values, and the blue ones are the observed data. So and you want to make sure that there is not like some systematic difference in the distribution. But here looks relatively okay, right? So again, we will look at other data later, and so hopefully you get a little bit better sense of that. All right, so okay, I've given you a little bit more information here. So that is, I don't want to spend too much time on it, so you can read over it on your own. So this is just for actually for using the multiple imputation results for your later analysis. So if you actually want to do an analysis, and we were talking about how in multiple imputation you're actually combining all the results from the 10 imputations, and you take that into account when you estimate your parameters for your actual analysis, right? So this is the example where we just some arbitrary things. So what we're doing right here is we are fitting a regression model. So, and that is described here. So what we are doing is we're predicting time DRS. So that's our outcome variable here from at house and income. So we're using these are basically multiple regressions. So we're using two predictors to estimate, so to predict so time DRS. And and based on our 10 multiple imputations, right? And what you're getting is so you have here it will give you the results for all your 10 data sets that we have created, and then you can pull these results into like one estimate, right? So of the parameters, and that is you can do by the function pool, right? So first you have to describe the model here, and actually do the estimation for all your, in this case we had 10, right? 10 imputations, or 10 data sets. And then later you pull the results and come up with some one pooled solution, right? So that is taking all these 10 imputations into account to estimate your true parameters, right? So, but again, so we will talk about that later in more detail. So, right, these are basically just your regression weights for estimate and for at house and income. So that is your basically your beta weight here in the regression. So it's 0.31 and 0.21. Then it's the corresponding standard error, right? So it's a t-statistic here, and then you have the p-value, and you see here that at house is a significant predictor of time DRS, but income is not, right? And this, as I said, so this is a combination of all the 10 results. Okay, so just very quickly, I just want to, before we talk about assignment 3, I just want to give you an overview what is what's going on in the rest of the tutorial here. Well, it's basically how to detect outliers in a data set. And in order to detect univariate outliers, always good to plot the frequencies, so the frequency distributions of our individual variables, right? And so we can do that just using the table function here, right? So we are basically just collecting the frequency distribution for all variables in our data set in a list here that is called FricTab. And and then we are plotting that, right? And then it gives us for each individual variable so as a frequency distribution. You can see, right? So you have here the possible. So the first row, it's a little bit hard to see because it has basically it keeps printing it in the next row. So here you have the possible values, right? These are the possible values, so all observed values in time DRS. So it continues here. That's from 0 to 81. And then here you have the number of cases for each value, right? So 42 participants have a 0, 44 have a 1, 67 have a 2, 52 have a 3, etc. Now, and then here at the same, just you see for at drug, so it's just between 5 and 10. And then at house you have 2 and 235. And then you have right? For income, you have this 1 to 10, and you see that's a huge proportion here, so a huge number in the lowest income category, etc., etc., right? You see the employment status distribution and the marital status distribution. So it's coded 0 and 1, it's coded 1 and 2, it's coded 1 and 2 too. All right. So, and then we also discussed last week how for continuous variables, outliers can be identified as those values that have a huge z-score, right? So huge standardized score. And so what you can do to just standardize all your scores in the data set is to use a scale function. You just have to make sure to omit any NAs. So before you do that, otherwise it will throw an error. So if you want to convert everything into z-scores, right? So you entire all variables on your data frame, you just basically put it as an argument, give it as an argument to the scale function, and then you have the z-screen data frame, and then you can define outliers that have extreme z-scores. You could say, okay, so the ones that are right out basically above the 3.3 standard deviations, plus and minus the mean. So we know that's only 0.1% of our data. And so, and then we can just print out so the cases for which that is true, right? And so we basically see here that so these are our, let me just quickly look. So for income, it didn't make sense, so I didn't do it. So for house, okay. 1 second. Okay, so what it is doing here, it's basically, so it always gives you so the entire row, so all basically all the data, all the other values and all other variables that have extreme, so for if one case has an extreme value in one variable, so that basically if you set it up like this, it will give you the entire row, right? So I'm trying to understand the output myself. So basically the way it's organized is, so here you have the results for time DRS. So basically, so these are all the the different cases, that 11 in total, right? So that have extreme values, so that are outside of this range, right? So on time DRS, and you see, right, it's 4.674425 for time DRS, and it also basically what it also prints here are the z values for all the other variables, which are in this case not that extreme, right? So, and it's here ordered. So basically, right, you see here it's also 3.68. So these are all higher than, so they are more than 3.3 standard deviations above the mean. And you can see, so right, it's always giving you also the z values for this case on the other variables. So sorry, just to make sure that the output is clear, right? So, and then the same for race. So that is just printed in a new line because it didn't fit here anymore. So that is all for the variable time DRS, right? So these are the cases that have extreme values on time DRS, but it prints basically all the other values as well. Okay, so for @drug, there were no extreme cases, and for @house, there were only 2 cases that have extreme values here on @house. So these are these were most likely the two really low scores here. We saw that 2 have just the number 2, and then the next value is 11, right? So these are apparently 2 extreme outliers here. So, and then the others don't have any extreme values, the other variables. Okay. So, and then, so this is just so a way to define multivariate outliers based on the Mahalanobis distance. And so it's implemented in R, so the function Mahalanobis. So, and again, so the difference is here that is a multivariate outlier. So it's basically an outlier defined on the basically all variables that are in the data set. So all variables in parallel considered. And so remember, so there was a centroid. The centroid was basically the combined mean of all variables in the data set. And then, so basically the Mahalanobis distance is measuring the distance of an individual data point from this centroid, right? From this combined mean. And again, you can, so what you see here in the output is always as a case number. So that has been defined as a multivariate outlier, and then the corresponding distance itself. And so the Mahalanobis distance values follow a chi-squared distribution if all variables are normally distributed, and that's why you can use a chi-squared distribution to define whether something is like significantly, so basically deviates more. It was an extremely rare case, right? So in this case, so that is a value that is that you should observe only 1% of the cases if you draw from a multivariate normal distribution. Okay, so that is shown here, and then of course we can, in order to check for normality, we can do our plots, right, or normality plots. So which we're, right, it's just what we did before when we are talking about ggplot. So note, right, for the binary variables, of course, you see, so that looks a little funny here because you have only two potential values. And so then you can also plot your QQ plots, which are very, very helpful, right? And you also see again, so time DRS has this clearly clearly strong deviation from the normal distribution, whereas for EDRAC, at least as far as we can tell here, it's a little bit, so the scale is a little bit limited, and for EDHAUS, except for these two outliers, it looks pretty good, right? So income is also like a little bit, it's a little bit overrepresented here in the lowest category, but apart from that, looks okay. So it's probably some bottom and ceiling effect. So, all right. And so this is just an overview of transformations. So what you can do with your variables if you detected deviations from normality, right? If you have a skew in your data. So, and all sorts of other issues, right? So what I have demonstrated here is for the time DRS variable to do a logarithmic transformation. And so you can see here that it basically gets rid of this problem. So the skewness and kurtosis is pretty normal now here. And so this is just a syntax for a few other common transformations and situations in which you want to use them. So just to give you like a basic overview. Alrighty, so yeah, as I said, we will go over all these steps when we are talking about the individual statistical methods. So we will repeat that. Right now, it was just an introduction into how it works in general, and so to give you like a little bit an overview of the syntax that you're using to do it. Okay. Alrighty. If you don't have any urgent questions, and I would say, sorry, it took me really long, that we talk about assignment 3 now and your questions that you had, or any other questions. So
because I didn't know how to pull descriptive stats until just now, and I was like, oh, that kind of helps a little bit with part of 1. But I kind of like skipped around. How do you get the weighted mean? Like, what's the code for that?
sorry, what number are you? What number?
I'm on one. I'm on one, but I
1A?
was skipping around. No, I was skipping around and I've done other stuff. So like I did 3 and part of 2 and stuff like that. So yeah. Weighted mean though, that's through that the descriptive stats in R can give you the weighted mean, or do you have to code for a weighted mean?
Yeah, that depends. I mean, what are you using it? Why do you need that for the assignment?
Because it asks what's the weighted mean for for the gender.
No, you don't need a weighted mean. So the weighted mean is basically if you give each, so normally if you calculate the arithmetic mean, so each case has the same weight, right? So they all have weight of 1, or I can also say every case has weight of 100. So, but every case has the same weight. If you calculate a weighted mean, so that means you give usually means you give different weights to, so different observations, but so you or different values. So, but you don't need that for this assignment. So you're supposed to do the arithmetic mean, which is just a regular mean.
Oh, I read that as weighted mean. I'm sorry. So you just want mean. Okay. No, arithmetic mean is B, but A says mean weight, and that's what I thought was we had to get weighted mean.
Yeah.
So
mean weight means really there's a it's a variable weight. So maybe there was a limit confusion. So.
Okay. Well. Okay. So what's the difference between mean weight and I don't know, arithmetic mean is arithmetic mean. It's goodness gracious. But weight as in like how much a person weighs. Oh my goodness, I'm about to edit this right now. Thank you.
All right. I hope that makes it clearer. So if there are questions like that, so ask me if things were confusing, right? And I have no idea what do you mean by mean weight. what do you so then, right? So it's then we can clarify that very quickly. So the mean of the variable weight, sorry for being not 100% clear. Okay, so alrighty, super. Does it make it easier? So is it now clear what 1A is asking for, or all right? So who else? So does everyone know how to do 1A, or what I'm asking for in 1A?
Mm-hmm.
Yeah.
Can you clarify when you mean combination of the variables?
Yeah. So marital status and gender, so both have like different so have like a range of values, right? Marital status, I don't know, it's like it could be like married, single, widowed, so they have like, let's say they have 6 different categories or 5, and then gender has I think 2 only here in this data set, and it basically means each, so basically for each value of marital status. So I want to break it down by gender. So married male, married female, divorced male, divorced female, single male, single female, widowed male, widowed female, etc. So yeah, I don't know. No, I'm not. Daughter wants me to put that on. No, it see. Okay, it's not visible, Arn. Dankeschön, mein Schatzel. Yeah. So it basically just means the combinations of all values of the 2 variables, so all possible. Yeah, does it make sense?
Yes, that makes sense. Thank you.
Okay. So and then it's a little bit, so the only difficulty potentially for 1A that I thought might be, so it's that there are a lot of NAs. So and you have to deal with those, right? If otherwise it won't calculate much. So because you have either in one or the other variable a lot of NAs, so you have to deal with the NAs first. Either you have to make some explicit values, or you do like the NA omit first. So whatever works for you, right? So I won't deduct points for that. I'm not expecting like a certain way you handle the NAs, but you have to sort of you have to do something with the missing values, otherwise you won't get it won't calculate the means for you. Yeah. So when we were talking, right? So in so when we had our tidyverse, right? So here, for example, right? So we so there's this option here to make the NAs explicit values, so they're just treated like a different response category. You can also use the NA omit function. So that is also possible. That was part of the tutorial today. So you can get rid of the NAs. I mean, there are basically a million ways to deal with it. Just make sure that you have to do something. Otherwise, you will have, just for your means, it will give you a lot of NAs because it cannot calculate. And then I will probably deduct a little bit. It doesn't mean that I will deduct the full points, but then I might deduct how many points are you getting? Nah, maybe 1 or half a point. I'm not sure yet. If the code is correct otherwise, but you haven't taken care of the NAs, then I might deduct half a point to a point.
For 1B, I'm unsure what you mean as proportion of female participants.
Naya, if you would, basically what I want you to create a new variable, and this variable is called gender2. And if you would then calculate the mean, if you would just tell our mean gender2, then I want the value that R spits out, I want that to be equal to the proportion of female participants in the sample. So for example, if we had like 30% women, then I want the command mean gender2 to print out 0.3. Make sense? Yeah, no?
It makes more sense, but I'm still a little confused.
So, okay. So gender has to be a dichotomous variable. I'm giving this hint. It has only 2 values, but I'm not saying anything else. Otherwise, I'm giving you the answer.
It's like coding for Excel. Think of it like that. Like, for example, like yes or no is 1, 2. And think of it like that for gender. Like 1 would be male and female would be 2 or something like that. So I think what it's saying
Something
for
like
gender,
that.
yeah, something like that. Yeah.
Yeah. Right. So, but that is the idea.
All right, I got it. Thank you.
Okay. All right. So any other questions? Yeah, so when here under C, when I say creates a new variable, so that doesn't have to be, you don't have to add that to the data frame, right? So, I mean, since you, no, sorry, that is not C. I mean, what did I mean? Wait a second. No, just forget it. Sorry, I was a little bit misled here. No, that is all, it's all good here. So that is basically all the different tasks. So they're just, they're what it's all in tidyverse. So you're almost everything. So it's just doing things that are in the tutorial.
For D, I didn't see anything mentioned on kurtosis
Yeah,
on tidyverse, but we talked about kurtosis.
yeah, today. So that was not in tidyverse. That's why I said so you can use the so either the PESTEX package or describe function from the psych package, or the stat desk from PESTEX.
All right, it was just confusing because we hadn't
Yeah.
learned about it until today.
Yeah, you can also. I mean, I'm as I said. So I'm sometimes a bit mean. So sometimes I'm also asking you to do things to figure out things on your own. So that's why it's homework. So let's just check whether. So okay, that is not alrighty. Okay, but I mean, you can there are many ways of getting these values, but so the ones that we talked about today are very easy, right? So because I spit out all the values in with one command. So either describe or PESTEX as a stat desk, and just make sure that you set the argument basic to false. Otherwise, I think it's not giving you the full range. Okay. So it's just a comment here. If when I say briefly explain what these descriptive statistics tell you, then I want you to show me that you understand them. So make sure that, I mean, that you don't have to write much, but it has to be meaningful. So basically what I want to see is that you understand what the statistic actually means. Don't say something like SD means this is a standard deviation. So that is not what I mean. So I want you to describe in your own words what the standard deviation is. It doesn't have to be like, right, super scientific, but I want you to basically, okay. So, okay, any other questions? What was difficult? So what other tasks are you struggling with? So this here is right. So this was something that you should use samples as the sample tutorial, sampling. What was it called? Sample or sampling tutorial. You have to use a slightly different function to select the, yeah, so to actually select the samples. Then in this example, but it shouldn't. Hopefully, it's doable to find it. Yeah, Nora.
Going back to G, I just wanted to confirm also that one we can focus on the lesson today on normal distribution, since we didn't learn about that much in previous lessons.
Yes.
Okay, cool.
So all right. So and then if you, I mean, what I would like everyone to do is to do the QQ plot. And so if you basically, if you just say it's not normal because they're not in a straight line, then I might not be super happy with the answer. So I mean, I was dwelling a lot, so I was, I was going crazy about the QQ plot. So I really wanted you to understand what it's showing. So try to interpret a little bit more than, right, just this, oh no, yeah, it's not a straight line. So what does it mean? So what are the deviations, and what does it mean? So where does the empirical distribution deviate from the theoretical distribution, and why? Yeah, at least tell me there are more, so we have more extreme outliers at the lower end of the distribution. It's a lower tail than the standard normal distribution, or more or fewer, right? So that's something that I want to hear. All right. Okay, other questions?
I did have a conceptual question about number 2.
Mm-hmm.
So I'm pretty sure I was able to manage to get the answer down, but I'm just more curious about the math behind it because I get the programming, but the math is still a little iffy to me.
Mhm.
Okay, so if we're making a sampling distribution, the one thing I'm not getting is, okay, say you run the for loop to create 10,000 iterations of the data sets,
Mhm.
then use the top number, but so is it just basically dividing the like five of the random, I mean 5 of the not individuals, I guess, randomly, and then create, or I'm just not sure how it's exactly how it's exactly generating the observations 10,000 times randomly.
Yeah, so what's the algorithm? So the algorithm is basically simulating that you are drawing 10,000 random samples from this population. So assume you have a bowl with 10 balls in it. And so they have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you get blindfolded. And and you're 10,000 times you draw 5 balls
Okay,
without
so
replacement.
by 5. Okay, I think
Yeah,
I
so without replacement. And so you do that 10,000 times. And each time you write down the numbers, calculate the mean, and you put them back. Right? Then you have a table that has 10,000 means. And then you can plot the distribution of your 10,000 means.
Okay.
That is your sampling distribution. And
Yeah,
the program is just simulating that for you, right? So it's simulating this random selection of the, it's actually never really random, but it's getting pretty close. The
Yeah.
computer, so computer software is getting pretty good at it.
Okay, yeah, that clears things up. Thank you very much.
Okay. All right, other questions? So I mean, the last thing is just right, yes, no. So I think that is not so hard. But anything else that's unclear? Right, so basically wants you to do some grouping first, obviously. So, so this is just right? Some conditional transformation. This requires a little bit. So here, ideally, I would like you to do that in R as well. If you want to do it by hand, that's fine. I would prefer if you did it in R completely. So with the formula that you're using, etc. If you want to do it by hand, it's fine too. If you basically just pull the numbers, your ingredients from R, and then do the actual
Calculations
by hand, that would be fine. But try to do it in R.
for 2 for the sampling. That's what, I'm sorry, you're pointing
No,
to.
not the sampling. Sorry, for the F one F.
Oh, okay. Yeah, I was trying to look for your cursor because I was lost. Okay,
Yeah.
for that one. Okay.
1F. Okay, so everything else, do you feel better about it now? Do you feel it's doable? Yes, no, maybe. So now is your opportunity to ask more questions.
Before, for number 2, I got it to run and now it's not running anymore. So like, I'm confused. But I need some time to work through it before I can identify what's going wrong.
Yeah. So the only difference is we had an example, right? Also in the script, in the tutorial. The only thing is that this is not a data frame; it's just a vector. So you have to use a slightly different. I mean, you could find other workarounds, but the easiest thing is you just use a different function to draw the random samples from this population. So that is the only thing that could be. Otherwise, you can basically do it almost the same way as in there. So you have to do this loop, And so the same way, just numbers are a little different. And then we don't have like whole data frame where we are like selecting cases. We just have, basically we have only one. You can also think of it as like one variable, right? So we're randomly selecting cases, but we are measuring just one variable, and this variable has the possible values 1 to 9. Rather than having like 50 variables for each case. All right. Any other questions? No? All right. So super. Okay, then yeah, so if you have questions about so the things that we didn't talk in much detail about today. Also, if you have questions, sorry, not the tidy versus screening, if you have questions about the code, if you basically, that's really important. I want you to do that. If you, for example, say, yeah, I looked at at this code here, so that is not so difficult, but let me find something that's maybe a little bit more. So for example, this here, yeah, so imputing the missing values with the mean per group, and I don't get it. I don't know what it's doing and what the logic behind the code is, right? So I can't grasp it, or it's just so post that. So I really want you to understand what the code is doing and why. So in the tutorials, and if you have questions about it, then ask them, right? But again, not say I don't understand the code, explain it to me. So then they say, well, so that is my idea, but I have no idea what does that mean, and what is this notation and why, right? So be specific about what's unclear about it. Okay, and sorry about that. I will probably revise it a little bit, because in one place I got the order mixed up, so I basically dropped the the code in one location, and here I actually wanted to replace. I wanted to call this here in this function to make it more readable, but I didn't do it. So I will actually change that to make it a bit easier for on the eye. Okay, yeah. So otherwise, if you don't have any further questions, then I would say let's call it a day. And anything else, the sooner you ask, the better, right? So don't ask me on Thursday. Ask. So if you're basically run into new problems, then with the assignment, then let me know soon. So that, because as I said, I cannot always guarantee that I'll be able to reply right away. Okay.
I'm getting an error that says stat bin requires a continuous x variable. The x variable is discrete.
Send me your code.
Okay. Should I send you it now, or like how do you want me to send it to you?
Send me an email. If I feel, I mean, basically you can also include, so you can, yeah, or you post it in the discussion forum. So your code
do that.
and the error message, ideally. So then everybody can see it and learn.
Okay.
All right. Okay. Yeah. Then yeah, thanks for listening. Not falling asleep. And so tomorrow we will talk about, yeah, that was also, if I apologize if there was like confusion. So my idea was that we are actually talking about correlations tomorrow. So that I just combine the so the methods for continuous and categorical variables, so into one class. And then next week we will continue with regression. And I will also post or send you the graded assignments as soon as possible. Okay. All right. Yeah. And so, and then again, so always let me know if things don't make sense to you at all, right? So if you feel you're just blind, so you're basically, if you feel you're not getting this R stuff at all, and you're just basically trying to copy the code, and but if if he feels more or less random, so that's not what I want, right? So then I will have to modify it a little bit, but I have to rely on your feedback. So if you don't tell me otherwise, I assume it all makes sense to you, and you get some better understanding of how it works. Okay. All right. Super. Then good luck with the assignment 3, and I'll see you tomorrow. Okay. Oh, Nora. So one more
Thank you.
question.
Yeah, so I went back
Yeah.
to the sampling R file that you had, and
Yeah.
I'm running through it again, and now it's giving me errors, but before it wasn't giving me errors.
So you mean from what we did in class?
Yeah, now it's giving me the same error that statbin requires a continuous X variable.
Yeah. So post that as well. Just
Okay,
post it.
yeah.
Post what you're, and ideally, yeah, we'll see whether I can reproduce it. I have no idea why.
All right, thank you.
Okay. Then good night.
Thank you. Good night.
Bye.
Bye.
See you.